Welcome, nocturnal minds, aboard. Your learning journey starts now. So, building on our previous discussion of Bayesian reasoning and simulation, we now turn to a fundamental question. How do we formally understand when evidence supports a hypothesis? This is the realm of confirmation theory. Think of it as trying to write down the rules for inductive inference, not just the black and white of deductive logic, but the shades of gray where evidence makes a hypothesis more or less likely. The big puzzle, the central challenge, is figuring out what it means for some observation, E, to support a hypothesis H, especially when E doesn't logically guarantee H. It's surprising this field took so long to mature, despite thinkers like Bacon and Mill grappling with related ideas. Part of the reason might be the lingering shadow of Hume's skepticism about induction. Can we really justify moving from past observations to future predictions? And more recently, Popper's focus on falsification cast a similar pall. But let's be clear, denying that evidence can support hypotheses is a form of radical skepticism. Without it, we couldn't rationally believe in an external world, other minds, or even trust our memories. Confirmation theory, despite its philosophical baggage, is deeply embedded in how we reason and make decisions. Now, when we talk about confirmation, we need to be precise. There are two main flavors. First, there's absolute confirmation. This means the evidence E is so strong that the total support for hypothesis H given E crosses some significant threshold. Think of it as saying yes based on everything we know, including EH is highly likely. Second, there's incremental confirmation. This is about change. Does adding evidence E to our existing knowledge base increase the support for H? It's like asking, does learning E make more plausible than it was before? Crucially, both ideas operate against a backdrop of all the relevant information we already have. So E being absolute evidence means the final score for H is high, while E being incremental evidence means the score went up because of E. Notice they can diverge. A positive AIDS test gives you incremental evidence you have AIDS, but it might not be absolute evidence. Maybe false positives are common. Our everyday use of confirmation seems to blend both these ideas. For the rest of this dive, we'll mostly focus on this incremental aspect, how evidence shifts the balance. Let's look at the early attempts to pin down these qualitative notions, starting with Hempel. He envisioned a step-by-step approach. First, get qualitative conditions right, then comparative, then quantitative. His initial stab at qualitative confirmation laid out 4 conditions that seemed pretty reasonable on the surface. Condition E: if your evidence illogically implies your hypothesis H, then obviously E confirms H makes sense. Condition R: if confirms H and H itself implies another statement, H prime, then E should also confirm H prime. Seems logical too. Condition Sen: if it confirms H and H contradicts H prime, then E shouldn't confirm H prime. Again, sounds right. Condition Si: if E confirms H and H is implied by a stronger statement, H prime implies H, then E should also confirm H prime. This also looks plausible, but here's the kicker Hempel himself recognized. If you accept all 4 conditions, you end up concluding that any piece of evidence confirms any hypothesis. Which is clearly nonsense. It turns out, conditions Yi and Si together are enough to trigger this explosion. So, something had to give. Hempel tried to patch things up by restricting condition Si, focusing only on cases where H is obtained by plugging in specific values, instantiation. But Carnap pointed out a deeper issue. Hempel was mixing up absolute and incremental confirmation. Let's dissect these conditions again, keeping in mind the distinction. For absolute confirmation, where H is already well supported, conditions E, R, and San seem okay. But condition Si still trips up. Knowing H is well supported doesn't mean H and X is well supported, even if X is true, unless X is already known and likely. Now, for incremental confirmation, the picture gets even murkier. Condition San, consistence clearly fails incrementally. Finding out E might increase support for H, while decreasing support for H prime, even if they contradict. Condition E, entailment works if H wasn't already certain, but if H was already probability E, then E can't incrementally confirm it further. Condition R, special consequence holds sometimes, but breaks down if E somehow strongly disconfirms H prime and not H while confirming H. And condition 是 converse consequence only holds under very specific circumstances, like when h prime is just h plus some irrelevant detail x. It seems these simple conditions don't capture the nuance of how evidence incrementally shifts probabilities. Okay, let's consider another angle, instance confirmation. Hempel also endorsed Nikod's condition, which sounds intuitively right for incremental confirmation. It says that, observing a specific case where both f and g hold like seeing a black raven, confirms the universal rule, all f's are g, all ravens are black. Finding one black raven makes the generalization slightly more likely, right? This seems fine incrementally, but then there's the equivalence condition, which is basically a tautology. If two statements h and h prime mean exactly the same thing, then evidence confirming, one must confirm the other. Also seems undeniable. Now combine these two seemingly innocent principles, and bam. The raven's paradox hits us. Why? Because all ravens are black is logically equivalent to its contrapositive. All non-black things are non-ravens. According to Nikod, seeing a non-black non-raven, say a white shoe, confirms the second statement. According to equivalence, it must also confirm the first statement. But wait, does a white shoe tell us anything about ravens? Intuitively, it seems utterly irrelevant. This is the paradox Hempel famously embraced. So, what's the deal with the white shoes? Hempel's response was radical. Just accept it. Our intuition is biased by background knowledge. We know there are zillions of non-black things compared to the few ravens. Confirmation theory, he argued, should abstract away from such practical considerations. But philosopher Ian Hacking pushed back, arguing that science needs confirmation theories grounded in reality, not pure logic. This suggests we need to bring background knowledge explicitly into the picture, making confirmation a three-place relation involving E, H, and Cower background knowledge. Once we do that, Nikod's condition seems to break down. W, Wei, O, Huan offered a different tack. He suggested Nikod's condition only works for natural kind predicates, terms like raven or black, that pick out objectively similar things. But non-raven is a grab bag of everything else, including electrons and galaxies. So, maybe the principle only applies to the former. Alternatively, perhaps the equivalence condition itself needs qualification. Maybe statements like all non-black things are non-ravens aren't really suitable for confirmation in the same way. These fixes feel a bit ad hoc, though. As we'll see, probabilistic approaches often offer smoother paths through this thicket. Let's shift gears to perhaps the most famous account, hypothetico-deductivism, or HD. The basic idea, championed by folks like Ayer, is that a hypothesis H is confirmed by evidence E if it follows logically from H, possibly with some extra assumptions, AE, AR, and so on. Think of it like this. If your theory predicts an outcome, and you observe that outcome, your theory gets a boost. The formal definition requires that the auxiliary assumptions alone don't predict E, but the combination of H and the auxiliaries does predict E. Sounds neat, right? Well, Doom and Quine immediately raised red flags. Those auxiliary assumptions aren't self-evident truths. They're themselves hypotheses, conjectures, potentially flawed just like H. This leads to a major problem. Confirmation isn't atomic. You can never confirm just H. You always confirm the whole package deal, the hypothesis plus all its supporting assumptions. This holistic view means there's no clean way to say whether the failure of a prediction is due to the main hypothesis being wrong or one of the auxiliaries. It also fuels the underdetermination problem. Multiple theories could explain the same data. Plus, HD struggles with statistical hypotheses, like fair coin tosses, since any sequence is possible. Clearly, HD needs refinement. This brings us to the probabilistic approach, which many find more promising. The core idea is to use probability theory as the framework for understanding confirmation. We start with a probability function. Let's call it P. Think of P as representing all the relevant background information, all the things we already believe or know about the situation. This function assigns numbers between Ling and Yi2 propositions, obeying the standard axioms of probability. What do these probabilities represent? P of H is the probability of H given only our background knowledge. P of H given E is the probability of H after we add evidence E to our background knowledge. Similarly, P of E is how predictable E is based on background knowledge, and P of E given H is how predictable E is if we assume H is true. This setup allows us to talk about both the epistemic status of a hypothesis and the predictive power of a hypothesis, all within the same mathematical language. With this probabilistic framework, defining incremental confirmation becomes straightforward. We say that evidence, E, incrementally confirms hypothesis H, relative to our background knowledge, P, if, and only if, learning increases the probability of H. In symbols, P of H given E is greater than P of H. Simple, elegant. Conversely, if P of H given E is less than P of H, is disconfirms H. And if they're equal, E is irrelevant to H. This simple definition has some nice properties. First, it tells us that evidence for H is always evidence against not H. If E makes more likely, it must make not H less likely. Second, it connects back to the HD idea. If H entails E, then P of E given H equals E, and assuming P of H is not Ling or E, P of H given E will indeed be greater than P of H. So HD confirmation is a special case of probabilistic confirmation. Third, it highlights the duality between evidence and prediction. E increases the evidence for H precisely when H increases the predictability of E. It's a neat symmetry. How does this probabilistic view handle instance confirmation, like the Black Raven example? It offers a refined version. A universal statement like, all F's are G for all X of X implies G of X is incrementally confirmed by learning that a specific instance, not of A or G of A is true, but only if two conditions hold beforehand. First, there must have been some positive probability assigned to the possibility that A is an F, but not a GP of F of A, and not G of A is greater than 0. Second, nothing else relevant should be learned simultaneously. The intuition here is that the observation rules out a potential counterexample that was previously considered possible. This probabilistic version avoids some pitfalls of Nikod's original condition. For instance, it handles the contraposit, all non-J's are non-F's, consistently and crucially. It depends on whether the counterexample was actually considered a live possibility before the observation. If P of F of A and not G of A was already 0, the observation wouldn't provide any new confirmation. This probabilistic take on instance confirmation actually helps dissolve the Raven's paradox. Remember conditions, nothing else of relevance is learned. In the real world, when we see something, we often learn more than just its basic properties. If I see a black raven, I might also learn it's a bird, or that it's flying, or whatever. This extra information, combined with our vast background knowledge captured in P, can significantly affect how the observation impacts the probability of H. Let's look at some scenarios sampling birds from a population of 1,000. Case E. Imagine we know either there are 950 ravens mostly black, or only 10 ravens all black. Seeing a black raven actually lowers the probability of H all ravens are black. Seeing a non-black non-raven raises it. Case E. If we know 998 are black ravens and the other two are weird, a non-black non-raven still raises P of H, but a black raven also raises it just less dramatically. Case E. If we know 900 are black ravens and the rest are white, but maybe some are hidden ravens, a black raven tells us nothing new about H, but a non-black non-raven does increase P of H. Case if here, a white non-raven actually lowers P of H. Case V, which is closest to reality, with few ravens and lots of uncertainty, observing a black raven gives a huge boost to P of H, while a non-black non-raven gives a tiny boost. The paradox vanishes when we acknowledge that real observations come bundled with context and background knowledge that shapes the confirmation. Remember the Duhem-Quine problem? When an experiment fails occurs, but H and A predict not, how do we know if it's H or the auxiliary A that's at fault? The probabilistic framework offers some hope here. The impact of the failed experiment on the probabilities of H and A depends critically on their prior probabilis, how likely we thought H and A were before the experiment, and on how well the different combination and ARD. AH and not A, not H and A, not H and not A predicted the outcome, E. It's possible for the observation of E to decrease the probability of H but leave the probability of A unchanged, or vice versa. It's even possible for E to increase the probability of H while decreasing the probability of A. Which outcome happens depends entirely on the initial beliefs encoded in P and the predictive relationships. So, unlike the holistic view, probabilistic methods at least provide a mechanism, however complex, for potentially differentiating the blame. Of course, figuring out the exact distribution of blame still requires careful analysis of these dependencies. Bayes' theorem is the cornerstone of probabilistic confirmation theory. It elegantly links the change in a hypothesis probability due to ever the left side P of H given E divided by P of H directly to the predictive power of the hypothesis the right side, P of E given H divided by P of E. This equation formalizes the core intuition. A hypothesis is confirmed by evidence to the extent that the hypothesis successfully predicted that evidence. It's a beautiful expression of the evidence-prediction duality. We can extend this to compare two hypotheses, H and H star. The theorem shows that the ratio of their posterior odds O sub E of H, H starred, their prior odds of H, H star, is exactly equal to the ratio of their likelihoods P of E, given H divided by P of E, given H star. This means the degree to which evidence E changes the relative plausibility of H versus H star is precisely equal to how much better H predicted E compared to H star. It's a powerful result showing the deep connection between updating beliefs and evaluating predictions. Okay, we know what it means for evidence to incrementally confirm a hypothesis P of H given E is greater than P of H. But how much does it confirm? Can we quantify this? Yes, probability theory gives us several tools. We can define measures based on ratios or differences. For incremental measures, we compare the probability after seeing EP of H given E to the probability BP of H. How much did it go up? We could use the ratio P of H given E divided by P of H, or the difference P of H given E minus P of H. Alternatively, we can define probative measures, comparing the probability of H given E to the probability of H given not E. How sensitive is the probability of H to the truth value of E? Again, we could use the ratio P of H given E divided by P of H given not E, or the difference P of H given not E. We can do similar things using odds instead of probabilities. This table just shows a few examples. The literature is full of different measures. Now, here's where it gets tricky. These different measures behave differently. Consider two principles. The law of likelihood says that the relative support of a piece of evidence E for two hypotheses, H and H star, depends solely on which hypothesis better predicted the likelihood ratio P of E given H over P of E given H star. The law of conditional probability says that the relative impact of two pieces of evidence E and E star for a single hypothesis H depends solely on the resulting probabilities P of H given E and P of H given E star. Some of our measures obey one law, but violate the other. For instance, the probability ratio measures satisfy the law of likelihood, but odds ratio measures don't. Incremental ratio measures satisfy the law of conditional probability, but probative ratio measures don't. This leads to apparent contradictions. Take the Ellen example. Ellen is picked randomly from a town with mostly Baptists, a few Catholics, and some Buddhists. Let's be Ellen is not a Buddhist. Evidence E. Ellen is a Baptist P of H given E equals. Evidence E star. Ellen is a Catholic P of H given E star equals. Incremental measures say E and E star provide the same amount of evidence for both increased P of H from 0.992 to E. But probative measures say provides vastly better evidence for H than E star does. How can they both be right? Joyce's solution is quite clever. These measures aren't rivals, they're measuring different things. When the incremental measures say E and E star provide equal evidence for H, they mean that both pieces of data cause the same absolute increase in the probability of H from 0.992 to E. They measure the change in belief. When the probative measures say provides much better evidence than E star, they mean that the current probability of H is far more sensitive to the truth of E than to the truth of E star. The difference between P of H given E equals E and P of H given not E equals 0.2 is enormous, while the difference between P of H given E star equals E and P of H given not E star equals 0.99198 is tiny. They measure the dependence of belief on the data. See the difference? One talks about the size of the step, the other talks about the steepness of the slope. Understanding this distinction resolves the apparent contradiction. It also helps with the old evidence problem. How can Einstein's theory be confirmed by Mercury's perihelion, which was known before? Incremental measures might say the effect is small because the evidence was already highly probable. But probative measures can say it had huge probative value because the theory made the previously uncertain data highly probable. This leads to a related principle often discussed, the surprisingness principle. It states that, holding other factors constant, evidence E confirms hypothesis H more strongly, the less probable E was expected to be. In other words, surprising evidence provides stronger confirmation than unsurprising evidence. This aligns with the intuition that unexpected findings carry more weight. However, this isn't universally accepted. Hempel himself argued that the prior probability of the evidence shouldn't matter for its confirmatory power. Others have challenged it too. Interestingly, even if people disagree on the prior probability of evidence, they can often agree on its probative value. Think about diagnosing a patient. One doctor might be almost certain Josh has strep throat, another might be very unsure. They'll also likely disagree on how likely a positive test result is for Josh. Yet, both doctors would probably agree that a positive test result strongly supports the strep hypothesis, while a negative result weakly supports it. They agree on the probative value even if they disagree on the incremental impact due to differing priors. So far, we've treated P as a given probability function. But what is it? One interpretation is the subjectivist or Bayesian view, represents an individual's degrees of belief or credences. Confirmation theory, then, is about how evidence updates personal beliefs. Critics argue this is too subjective, too tied to personal biases and history, and perhaps unsuitable for the objective enterprise of science. Bayesians counter that subjectivity doesn't mean irrationality. Competent scientists' beliefs are generally well calibrated. Furthermore, convergence theorems suggest that even with wildly different starting points, repeated exposure to the same evidence tends to bring people's probabilities closer together, lending an objective flavor. However, some philosophers want more objectivity. They seek interpretations of probability that don't rely on anyone's subjective feelings. The most prominent attempt in philosophy is the logical interpretation, championed by Rudolf Carnap. Carnap's dream was ambitious, to create an inductive logic, a way to determine the degree of confirmation universally, much like deductive logic determines entailment. His early systems worked within a simplified language. He defined state descriptions, the most detailed ways individuals could be described, and structured descriptions groupings of states by frequency counts. He proposed a confirmation function C of H and E, calculated as the ratio of the measure of H and E to the measure of E. His preferred measure M star treated all structured descriptions equally, and then distributed probability evenly among the state descriptions within each structure. This setup allowed for genuine inductive learning. Observing one force increased the probability of another individual being ph from E over R to R over sen. Later, Carnap generalized this into a family of functions, lambda parameterized by lambda. Lambda acts like a caution knob. Low lambda means trusting the data heavy straight, high lambda means being skeptical of induction, and infinite lambda means never learning. He saw choosing lambda as a pragmatic decision for each scientific context. But Carnap's project faced significant hurdles. First, his initial languages were too simple for real science. As he tried to enrich them, The confirmation relations became bizarrely dependent on the syntax of sentences, ignoring their meaning. This led directly to Goodman's devastating critique. Consider green versus grew, green before time, blue oft. Observing many green emeralds confirms, future emeralds will be green, but not future emeralds will be grew. Yet, green and grew are syntactically similar in Carnap's system. Any logical account needs to respect meaning, not just form. How could Carnap's system distinguish? By privileging some predicates over others. But how? Based on logic, Goodman suggested entrenchment, how much we've used a predicate before, but that feels arbitrary. Finally, the parameter lambda remained problematic. Logic couldn't fix its value, and trying to determine it empirically just kicked the can down the road, leading to an infinite regress. Carnap's later work adding more parameters only made the situation worse. The dream of a unique, purely logical confirmation function seemed to evaporate. So, where does this leave us? We started by recognizing that much of our reasoning, especially scientific reasoning, goes beyond simple deduction. Confirmation theory is needed to understand inductive support. While it shares some similarities with deductive logic, focusing on the relationship between evidence and hypothesis, not just their truth values, it differs in key ways. Confirmation isn't black and white, it comes in degrees. Meaning matters, unlike pure syntax. And there doesn't seem to be a single uniquely determined confirmation function, perhaps not even one derivable purely from logic. It seems we need at least a three-part relation involving evidence, hypothesis, and background knowledge. Despite these challenges following Carnap, we reject the skeptical stance of Hume and Popper. We believe that relations of confirmation are real important and worthy of serious study, even if finding a perfect theory remains elusive. The journey continues,